Okay, so today and tomorrow is going to be review of the semester. Today is going to be focused on the first two units, units 5 and 6. I'm going to be doing basically mostly focusing on sort of practice questions to go through and show you what kinds of material you could expect to be on the test. So, jump right in here to Unit 5. So, Unit 5, remember, was atomic and nuclear physics. And you sort of had things broken up into two categories of questions. You had fusion and fission questions and decay questions. Okay, so those are kind of your main groups of stuff. So let's uh, focus on that. The fusion and fission, that was the idea that we have. Um, you have some sort of nuclear reaction, either things coming together and fusing into a new thing, or things splitting apart, going through fission, and ending up with other things. And you find a difference in mass between what you started with and what you ended with. You convert that mass into energy, 3 equals mc squared. You can kind of do stuff with that. So, um, I pulled up uh, this here. So I just randomly picked livermorium. So here we have livermorium 292. Okay, so let's say we have liver. That's not even livermorium 292. Uh, Decays into, and you can just see the chain here. Uh, these alphas are helium 4 nuclei. So I'll just go all the way. So it's 3 helium 4s, and I think it's a Darmstadium. Yeah, Darmstadium 280. Okay. 3 helium 4 nuclei and 1 Darmstadt. Is that it's Stadit, right? Yeah, Staditium. 280. How much energy is really okay? So, what we do is we can look up uh, the mass values for each of these nuclei. So, let's go back to the livermorium. So, livermorium 292, we have here atomic, it says weight, but it's really mass. So that is our number that we want to use. Again, this you can use this website or you can use the Wikipedia article. Is periodictable.com, and then so here if you just go to periodictable.com. I guess you have all your list of stuff. So from there, I went to livermorium, and you end up with a page like this. And then from here, you want to go up here. It should say isotope data, and that's kind of where we go to get the numbers we want. So here we have because again, I'm assuming you can do this online, so I'm not going to give you these mass numbers. You can look these up. So this is a way to kind of look that up and make sure you get the right numbers. So livermorium 292 has a mass of that. Um, Helium 4 has a mass of something, and you can click here. See helium, yeah, helium 4. Whoops. And then Darmstadium 280. Or is it DM, not DS? It is DS, right? Yeah, okay, it was 280 though. So you remember, see, it defaulted to 281, so I want to go to 280 here. And that's the number I want. Okay. All right, so now what's our equation here? So we have livermorium 292, and that splits into 3 helium 4 and the 1 Darmstadium. Okay, so our equation here then is going to be 292.199786 turns into 3 times 4.00260325.415 plus 280.159795. Right, so calculator time. Well, this is still... Okay. Alright, so 3 times the helium. So 3 times 4.00260325415. Okay, that funness. Right, double space now. Oop, shoot. I guess it wasn't. Okay, it looks kind of weird. Okay. Plus 280.15975. Okay. So... Alright, so we have plus 280.15979. Right, I actually hit times. Okay, wait, hold on. Okay, ignore that. That's wrong. Okay. What did I do? I don't know what I did. Okay, just press numbers forever until something happens. Okay, 12.00780976245 plus 280.1599795. Okay, there we go. Right, so is this a decrease? It is. It goes 292.19, and this goes to 0.16. So there is a decrease. So our change in mass is now... I'm going to do minus 0.1996. Is, well, I guess, yeah, you lose that much mass. Again, the positive negative doesn't really matter here. I'm just going to get rid of it. So that is our delta M. That's our change in mass. Now, remember, though, this is in the atomic mass unit. So we now have to convert this into kilograms. 3755 times, and this is in the formula sheet, it's the 1.66054 times 10 to the minus 27. I'll write it down here. So, times 1.66054 times 10 to the negative 27. Alright. So this now is our change in mass in kilograms. And so now, to find out how much energy there is, we are going to need to put this into E equals, technically it's delta MC squared. So we have 5.3438222012277 times 10 to the minus 29 times the speed of light squared. I almost put times 10 to the 6 for some reason, but anyway. So squaring the speed of light, you have 9 times 10 to the 16. It's just kind of an automatic thing you can do. And this ends up getting you, so times 9 times 10 16. Oh, right. Oh boy, that's... I want to write this number in scientific notation because otherwise it's just annoying. Okay, so that's 3, 4, 5, 6, 8, 9, 10, 11. Okay, so that's 10 to the negative 12. I'll do this much. There. That's your answer. Nope, get the 4. That's how much energy would be released from one of these reactions. Now, and then I could go further. For example, I said, what if you had 1 kilogram of Bermorium-292? How much total energy would be released? Okay. So, the idea is that this is energy per reaction, so we need to therefore know, and each reaction starts with 1 livermorium atom. So in other words, 1 atom results in this much energy. So then we need to find out how many atoms are in 1 kilogram. Well, we therefore need to find out what is the mass of one atom of livermorium-292 in kilograms. Now we have the mass here in U. Let me just copy this here. So in kilograms, what number here? So we have, let's see, 292.199786 times 1.66054 times 10. All right, so 4.852 times 10 to the negative 25. That is our mass of one livermorium atom. So, how many atoms are therefore in 1 kilogram? You're going to say 1 over this. So just boop. Okay, and stupid. 3, 6, 9, 12, 15, 18, 21, 24. 2.061, I guess. Something like that. Yeah. So then, okay. So this is how many atoms we would have at a kilogram, and this is how much energy is produced per atom. So we would therefore take this number of atoms and multiply it by the amount of energy for one atom. And we get to this here. We get 3, 6, 9, 12. 9.912. That much energy is released. Okay, so that's sort of it, I guess. That's the main thing you need to know for that. Just kind of dealing with the mass numbers and putting them into equals MC squared and all that fun stuff. And yeah, that's just different variations of that question, kind of get you for what you need for that. So the other type of question is nuclear decay question. And actually, we can just kind of base it off of this too, because this is a naturally decaying process, right? Well, here, let me get out of the. Okay, 4 minutes. Wait, no, that's 281. I want livermorium. Okay, 18 milliseconds. All right, cool. Working on half-lives of milliseconds. Okay. Well, there's two ways to go about this, right? We have. Here's the formula sheet. Let's see, because we have. Right. So we have this formula for decay and this formula for decay. This one we want to use if we're solving for how much is left, and this one works if we are solving for how much time has passed. So I'll do two different questions for either of these. So let's say how many was it for? 18 milliseconds. Okay. Oh well, here I'll say if you start with 1 kilogram. After 1 second, how many atoms are left? Okay, so since I'm asking for number of atoms, I should use for my starting value not 1 kg, but I should use the number of atoms to start with, which is, yeah, this many atoms in 1 kg. So this is the number I should start with. That should be my N0. Because the formula I have right is N over N0 equals 1/2 to the T divided by, is it alt 952? Nope, that's theta. 955? Yeah, that's it. Okay. So what we have here. So the numbers we have, we are solving for n. N is how much we have left. So n we want. N0 is going to be the number of atoms that we start with. And T equals 1 second. And the half-life is 18 milliseconds, which is 0.018 seconds. Yeah. Yeah, okay. So, plugging this in, then we get n I'm just going to multiply the n0 to the other side, so it becomes like this. Oftentimes, you don't really care about n0, and it's just sort of like you have 10% left or something. So that's, fine enough, but here, since we have an actual number, I'm going to do this. And so, okay, n0, 2.061 times 10 to the 24 times 1/2 to the, all right, 1 divided by 0.018. All right, so I'm going to resolve the exponent first. So we have n. Okay, it's the exponent, so we have 1 divided by 0.018. Boy. Okay, 55. Repeating, all right. So now I want to do 1/2 to that power. Okay, so it's a 0.5 to 55 point. Do this for a while. All right, good enough. Oh boy, that's a small number. Okay. It doesn't round well. I'm gonna go all the way to here actually, because again, since when you get numbers this small, it does actually kind of matter. We have that, and it's times. And this is negative 17, I think is what it said. Yes. Okay, so then n equals. All right, so we have. Almost 39 million atoms. That's our answer. So we started with like a billion squared, and we ended up with 38 million after 1 second. So, yeah. Yeah, there we go. So there's our answer for that. Another thing you could do is an opposite question could be how much time passes until you only have let's say 1,000 atoms left. Let's say that. How much time passes until you only have 1,000 atoms left? So now we're solving for time. So we're going to want to use the other equation. The other equation being this one here. Oh wait, I want to. Yeah, okay. Let's see. Time we don't know. That's what we're solving for. Again, lambda we do know. That is that many seconds. N is 1,000. That's saying that's how many atoms we have left. And 0 is 2.061 times 10 to the 24. And yeah, that's it. Okay, so we have. Oh boy. T divided by 0.018 equals the log of 1,000 divided by 2.061 times 10 divided by the log of 1/2. Okay. Let me figure this out. So we have divided by 2.061. Yes, okay, so we have 4.852 times 10 to the minus 22. Actually, that number should just be from what we had up here, right? Yeah, that's just that number. Okay. 8,000? Oh, because yeah. Okay, yeah. Okay. Never mind. And then that's divided by log 1/2. Okay, so now we have to turn both of these into logs, or we have to resolve the logs. So t divided by 2 equals. Okay, so the log at the top here. Okay, so log of this Okay. And I normally don't want to round this, but since this goes to 99, I'll round this up to 0.078. Okay, and then log of 1/2. Yeah, similar thing, it goes 999, so that there, and this becomes 3. Okay. Yeah, using negative 0.30103 as a stand-in for log of 1/2 is usually good enough for like almost anything. So then we got to divide this. We have negative divided by negative, so we don't have to worry about that. So we have 21.314078 divided by 0.30103. All right, so we have. I'll run to this. A little bit better about it. Okay, so then t equals 70.8038335 times 0.018. So t equals how many seconds? 1.27 seconds. So barely over a second. Second and a quarter, basically. So there you go. You go from in 1 second you get to 39 million, and then another quarter second you go down to 1,000. If you did solve this for 1, I wonder kind of what you would get. Well, actually, you would do the exact same thing, except it would be 4.852 times 10 to the minus 25, and then you would do the same thing. You know what? I'm just curious. What do you get if you do that? 4.852. Yeah, you get that, and then you want log of that divided by 0. 1.45 seconds. Yeah, okay. So you end up with 1 atom left after less than 1.5 seconds. So that's fun. Yeah. So there's your kind of ridiculous example for that. But that that kind of covers all you would need to know for this. So we have sort of fusion. Well, it's a fission question, but fusion is the exact same. It's just same methodology anyway. And then solving for energy from one reaction, then energy from a total number of reactions. Here's a decay question where we have the time and we're solving for the amount. And here's a decay question where we have the amount and we're solving for time. And that's kind of all you could be asked about for Unit 5. So we're kind of done with Unit 5. Now, Unit 6, I want to kind of keep, yeah, okay. So, Unit 6 was waves, sound, and light, kind of more specifically. So we have, well, there's the main questions for this is we would have standing waves, you would have decibel questions, you could have black body questions, and also Doppler questions. I think those are kind of the main thing. Let me look at the formula sheet here. So yeah, we have, yeah, because here's the pipe stuff, or the standing waves. Then we have your intensity decibel level. There's your, wait, there's the energy from the atomic energy stuff we could get at. You know what? I'll put that in there. What was that just called? I guess like atomic energy. Yeah. Oh, it's atomic spectra. Yeah. And then yeah, peak wavelength and the other thing. Yeah. Okay. Yeah. So, these are kind of all like related to each other in some way. Well, you have the wave equation all throughout. So let's start with the standing wave question. Let me just, I don't know, come up with something. What's something that's like large? How long is like a jump rope? 2 meters? That standard length of a jump rope? I feel like they're shorter than that. Because like I feel like if can you hold like a jump rope like out stretched like with your one end with each hand and kind of actually have it stretched out tight? Can kids usually do that? I don't know. Because if it was 2 meters, like a kid couldn't do that. I'm gonna say 1.5 meters. You have a 1.5 meter long jump rope. The wave travels along the jump rope at. I'm gonna be really easy and say 1 meter per second. No, it won't be that easy. I'll say 0.8 meters per second. No, that's not right. That's way too slow. I'll do 1.2 meters. No, I'll say 1.2 meters per second. Okay. Find the frequencies needed to produce the first 3 harmonics of standing waves. Let's do that. Okay, so it's a jump rope. It's a string, right? So that's a string. So you would use the standing wave of a string equation, which is here f string. Where's my mouse? There it is. This here. So nv over 2l. So we have f string equal nv over 2l. Okay. So and we want we want the frequency to produce the first 3 harmonics. So n is going to equal 1, 2, and 3. V is the speed of the wave, and we have that. The wave travels at 1.2 meters per second. And we have L, that's the length of the rope, which in this case is 1.5 meters. And we are solving for F. We're solving for that. Okay, so we start with the first one. So n is 1 times the speed of 1.2 divided by 2 times 1.5. So this becomes just 1.2 divided by 3, which is just what, 0.4? Why did I close the calculator? I'm a dingus. Okay. Yeah, 0.4. Okay. And then second harmonic, 1.2 divided by 2 times 1.5. This becomes 2.4 divided by 3, which is going to be 0.8 hertz. You know, also a quick way to do this is that the second harmonic is always just twice the first one. And then the third harmonic is 3. So we have 3.6 divided by 3, which is just 1.2 hertz. Just get 3 times that. Okay, so that's an example of that. You could also go backwards. It could be a question where it's like, hey, if I have a frequency, you know, let's say here, if I have a jump rope where the, why did I put an I there? I'm weird. Jump rope. Wait, no, it is a J. It just wasn't. I'm stupid. Okay. Where the fundamental frequency was 0.5 hertz. How long is the rope? Okay. So now, same equation. Still, a rope, a string. It's a fundamental frequency, so n is 1. V, I'm just going to use it as the same number as before. L, we don't know what we're solving for, and F is 0.5. So now we have 0.5 equals 1 times 1.2 divided by 2L. So you can multiply the L up, so you get, and divide the 0.5 down. So you get L equals 1 times 1.2 divided by 2 times 0.5. So this becomes L equals 1.2 divided by 1, so it's just, well, 1.2. Here's your answer. That makes sense, I guess? Yeah, no, it does make perfect sense. Yeah, okay, so, yeah. So I feel those are pretty straightforward. Okay, so let's move on to another question then. Let's see where we are now. Decibel questions. Okay. So You kind of go multiple ways with this. Let's try. Okay. A speaker has a power output of 0. I can't type. 0.05 watts. If you are standing 3 meters away, what decibel level do you hear? Okay. So, I'm asking for decibel level. Decibel level is this equation here, right? Yeah. So, but we need I. We need I. So I is power divided by 4 pi r squared. Okay, now power, we have that. That's the wattage. So power output is 0.05 watts. And we have r. That's our distance away. So it's 3 meters. So we can solve for I. Because we have the power 0.05 divided by 4. And then 3 squared. So 0.05 divided by 3 squared is 9. So times 4 is 36 pi. So what does this end up being? 5 divided by 36 divided by... Where's pi on this thing? Oh, it's up there. Okay. Great. I'll go to here. It was 10^4? Yeah. Unit for intensity is watts per meter squared. So that's going to go then into the decibel formula. So divided by 10 to the negative 12, that means that just this, it's going to be negative 4, 10 to the negative 4 minus 10 to the negative 12. So it's going to become log 4.42097 times 10 to the 8. So you see if we divide this by 10 to the negative 12, it becomes, yeah, that's to the 8. So we want the log of this, and then, well, it's times 10 of that. We have 8.6455. So our answer is 86.455 decibels. There you go. And you could also go backwards. It could say, let's see. How close must you be for the speaker to sound like 100 decibels? Use that. So now we got to go backwards. Same setup for everything here, except we don't know what the distance is. We're solving for that, and we know that the decibel is 100. So we have 100 equals 10 log I divided by 10 to the negative 12. Okay, so 100 divided by 10 equals 10 log. To get rid of the log, this becomes whatever is inside of the log is equal to 10 to this. So this becomes 10 to the 10 equals I divided by 10 to the negative 12. And so then you're multiplying. For this to work, I has to equal 10 to the 2, and we're just 100. Or no, to the negative 2. Sorry. Because if you multiply it, so 10 to the 10 times 10 to the negative 12, so 10 minus 12, so yeah, 10 to the negative 2. Okay, so that's your intensity. So then this is going to go into this here, in your intensity, so you have 0.01. Okay, so we have, yeah, so our power is still, what is it, 0.05? Yeah, 0.05 equals 0.05 divided by 4 pi r squared equals 0.01. So, okay, we can cross multiply, cross divide here. So we have 0.05 divided by 0.01 equals 4 pi r squared. So that becomes 5 equals 4 pi r squared. So 5 divided by 4 becomes 1.25 equals pi r squared. So r squared equals 1.25 divided by pi. Ah. 1.25. Okay. So that grossness. This. No, give me the. Okay. So then r is the square root of that. 0.63. Okay. Yeah, and that. So again, kind of showing different things you can do for decibels, going in either direction to get what you want to get. Okay, what's next that we got here? Black body questions. Okay, and then also atomic spectra kind of relates. Okay, so black body. Let's see. Actually, I'm going to kind of combine these together. So, now the atomic spectra question, you need an energy number, and the thing is, from the last unit, we have one. We have this. This was the energy that we got from a nuclear reaction. So let me hold on. So the that's right, Livermorium-292 reaction resulted in of energy being emitted. How? Wait, no. What type of light is this being emitted as? Okay. So in order to solve for this, to know what type of light it is, we need to know its frequency or its wavelength. Now we have the equation here that links frequency and energy. And we also have what h is, it's this here. So we know E equals h, that's not what I wanted, hf, and E, we have that. And h is 6.63 times 10 to the negative 34, I believe. Yes, okay. And we're solving for frequency. So we have 4.80944 times 10 to the minus 12 equals 6.63 times 10 to the minus 34 times f. Okay. So f is going to be, we have to divide that there. Okay. Yeah. So let's get to dividing. Okay, 4.80944 divided by 6.63 equals. Okay. Okay, I'll go 0.7. Now and then times the exponential here. Negative 12 divided by negative 34. So that's 0 minus 12. And it's minus 34. So it should be, well, okay. 0 minus 12 plus 34. 22. So it's that, but again, the scientific notation is wrong, so this should be, and this is 21. Yeah, okay. So that's our frequency. So what type of light is that? You can look at the chart. And frequency, anything over 3 times 10 to the 19 is gamma. So this is 3 times 10 to the 21. So this is a gamma Okay, now to combine this with the black body. So follow-up question would be, what temperature would you need so that the peak wavelength would be this light? Okay, so the equation for this is what we have here, is that the peak wavelength equals times t times the temperature equals 0.003. So okay, now T we're solving for, right? What temperature do we need? Now we don't know lambda either, but what we do know is that frequency times wavelength equals the speed. And in this case, let me actually get that down there. And here we know that the frequency is what we just solved for. And we know v is, since this is light, is the speed of light. So we can solve for the wavelength and then plug that into this and solve for temperature. So the wavelength times the frequency equals the speed of light. So divide the speed of light by the frequency. Okay, so we have 3 divided by 7.254. Another small, or something that's less than 1, which is annoying. Just paste it, but I'm lazy. Okay, so then it's times, and this becomes 8 divided by 10 to the 8 divided by 10 to the 21, so 8 minus 21, which is 13 minus 13, right? Yeah. But since we gotta, again, change this into correct scientific notation, so this becomes 14. Okay, so that's our wavelength. And that should still line up with this here, because it's less than, yeah, okay. So, okay, so now that we have the wavelength, we can then plug that in to the temperature equation. So, yeah, equals, okay. So we have 4.13564 times 10 to the negative 14 times temperature equals 0.003. Okay, so the temperature equals 0.003 divided by 4.13564 times 10 to the minus 14. All right. Just gotta divide that out. So 0.003 divided by 4.135. That's not a 5. 564. Okay. Negative. Yes. And we end up with a temperature of 72.54 billion. And that's, so there's your temperature, which is an unreasonable temperature for like anything to be at. So there you go. That's a good example of combining this kind of stuff together. So yeah. Okay, what else do we got here? Do we just have a Doppler question left? I think we do. Ooh, oh boy. Let's do a speed. Let's do a speed of sound one. So let's see. Yeah. Well, let me look up the musical note kind of thing I was looking at before. Frequencies of, yeah. Yeah, that's what I had before. Okay, so let's pick a note. Here's the A4, the standardized A4. Okay, so wait, I know. Hold on. 28. What? Interesting sentence there. Okay. Let's say 28 miles per hour. Wait, okay, hold on. Miles per hour to. Okay. 28, this becomes 12.5. Okay, I'll use 12.5. Okay, so, Usain Bolt is running at you at 12.5 meters per second while singing A4 note with a frequency of 440 hertz. What frequency do you hear? Beautiful. Okay. I don't even know what the guy sounds like. Like just talking. Okay. So what's the formula we have for this here? Here's the formula we have. Okay. So, what numbers do we have here? So VW is the speed of the wave. Okay. So this is sound. He's singing his beautiful angelic voice, presumably, and that's 343 meters per second. He's also the speed. Vs is the speed of the source, so that's how fast he's moving. So that is 12.5. And we have F, which is 440 hertz. Okay, so we're solving for F prime, and also since he's running. So okay, we're solving for F prime. We have 343 divided by, and he's moving towards you, so it's minus. Okay, so 343 minus 12.5. 330.5. So okay. Yeah, I'll run to here. $456.64. Is that enough to actually register as a higher note? Ooh, wait, was it 56? It was 56. Ah, not quite. Okay, it's like a quarter tone. Almost. Kinda. Sort of. Sorta, kinda. Ish. Yeah, it's almost like a quarter tone. Okay, interesting. Okay, so then a follow-up question, a different question would be, well, okay, you could actually go further. So, okay, if he runs past you, now, I can't type. What frequency do you hear? So now he's running past you, he's going away from you. So everything is exactly the same in terms of the setup here, except this is now a plus. So this becomes 343 divided by 355.5. Point. Great numbered around 2, but all. $424.53. And again, that's not. Yeah, still about a quarter tone. Okay. Okay. However, I'm gonna different thing. How fast would he have to run for the note to sound like a what's the oh they thinged it. Okay. A sharp 4, which has a frequency of 466.16 hertz. Okay. Now, it doesn't actually specify if he's running towards or away from you, but this is the noise you hear. This is a higher pitch than the noise that is actually being made. So in order for that to happen, he has to be running towards you. So again, the same formula set up here. But he must be running towards you in order for this to work. If you're not sure and you try it, and you do it the other way, you'll find that it literally does not work mathematically. It doesn't make any sense. So, okay, so because what numbers do we have here? We now have that f prime is 416.16 hertz. We know VW equals 343 still, and we know that f equals 440 hertz. We're solving for Vs. So we have 466.16 equals 343 divided by 343 minus Vs times 440. Okay, so if we divide 440, so we have 466. Okay, we have that, and that's not a great. That's an annoying number because to round. Pooey. Okay. You know what? I'm gonna be lame and write 0.06. I don't like rounding that much, but I'm at least gonna write it that way. You have 343 divided by minus s. Okay. Then we can cross multiply here. So the 343 in the denominator can come up over here, and I'll divide the 1.06 over. So I have 343 minus Vs equals 343 divided by 1.06. Okay. That rounds better. Okay, and then you can kind of see how this should work. So 343 minus something equals this. So therefore, minus, yeah, the non-negative version of that. So this should be a 5. There's your answer. Meters per second. And actually, just I'm curious, so 19.245. $43 miles per hour. Yeah, okay, that's reasonable. So if you run 43 miles per hour, it'll make your voice change by a half step. Woohoo. Again, it's a half step, so it's not even much. If you want to do a whole step, that'd be even more different. You know what, now I'm curious. What is it if it's a whole step? So here, you know what, follow-up question. Let's do it. What about a whole step to a B or at 493.88? Again, just exactly the same math. It's just now this becomes 493.88. Oh, annoying crap. 1.122. Again, you can switch it around, so S equals 3.3. And that works. To make it all line up right. And so you get 37.42. which let's convert this. 83 miles per hour. Sweet. Okay. So, yeah. Um, yeah, again, keep going with this. So, there, it pretty much covers any type of question I could think of asking you. I could, I guess, make the scenarios a bit more complex, but, like, I don't really, especially for these kind of questions. Well, okay, so for waves, I really don't know what else I could do in terms of making it more complicated. I guess in terms of, like, standing waves, I could make the n be kind of not what you're used to. Um, I could, besides that, I don't know what else to do in terms of this kind of stuff, in terms of making things more complicated. The atomic stuff I could definitely make more complicated by just having, like, having this thing be, like, way grosser. That's certainly something I could do, um, which I probably will do. So yeah, but besides that, I don't really know what else I could really do. Um, so you should kind of know what to expect for these kinds of things. There really isn't anything new to go over for that. Yeah. So I guess tomorrow we'll continue on with Unit 7 and 8, showing you some electricity stuff, and then what kind of questions for the astronomy things you could be looking into. So yeah, there's sort of both of those kind of have their own two main groups, because electricity there was the fields and the voltage stuff, and then there was the circuit stuff, and then astronomy. Um, there is some stuff that I'm gonna want you to know about, like the HR diagram, like what kind of stars go where. But in terms of like math questions, you basically have like the transit graphs and relativity. So yeah, kind of it. What you got for that? Oh well, there's equilibrium temperature too, but I mean that's related into the transit graphs. So yeah, but I'll show examples of that tomorrow. So yeah, hopefully you kind of know what to expect with this going forward. Maybe this might have been fast, but again, if it's since the video, you can always kind of slow down and stop the thing or whatever. So hopefully it's not too terrible. I mostly just didn't want to be recording this for like 2 hours, so that's why I kind of on purpose was going a little bit fast. But hopefully it was not the worst thing ever. So yeah, see you tomorrow for the other 2 units.